Right, so I want to go to chapter 13 first, and then if we have time, then we can go back to chapter 25. Because this chapter is really important, especially for people taking experimental fluid next semester for 273, and for many areas also. Complex numbers and complex analysis is very important. Right? So, in a complex domain, basically there is a real part and there is imaginary part. And any number can be represented by those two guys, the real part and the imaginary part. You can basically consider them as if the x coordinates and the y coordinates in a 2D domain, basically, two-dimensional world. Those will be your x and y. And you can write the number like this, 5, 3. Or you can make it 5 plus I3. And the I is the imaginary I, the square root of -1. So when you write the number like this, 5 plus 3i, you understand that the real part is 5 and the vertical part, the imaginary part, is the 3. Right? This is two ways to write this number, and there's a third way, the polar coordinate, that we're gonna speak about in a second. And so the problem in this chapter is basically very simple. It's actually, I will give you the complex number in an equation, and I will ask you for that complex number. What is it? Is it basically, I'm asking you to write it as 5 plus 3i. So how is that hard? So the problem would be something like this. You know, 5 is basically len z, where z is a complex number, or sine z equal 5. And then I'm asking for what is that z in terms of x plus iy. Okay, that's what we will ask for. What is the real imaginary part? Okay, it's basically, it's as if the equation is, you know, equation, kind of nonlinear equation in z, and we want to find that z. Right? And again, note that this z can at any moment be replaced by x plus iy. So if sine x plus iy is 5, what's x and what's y? Okay, that is the kind of problem that we have. So let's see how we're going to solve this. So again, the I is the square root of -1, and the I by itself, 5 plus 3i is a complex number, 3i is a complex number, I is a complex number. So I by itself is basically 0 and 1. If I tell you I, that's a complex number which doesn't have any imaginary and doesn't have any real part component, have only 1 as the imaginary component. Right? So it stands like this. That's the I. Okay? And so the sign of the imaginary part basically tell you whether you are on top or the bottom, of course. Right? And for example, if the number is 3 minus 3i, chances are it would be here. First, second, third, fourth quadrant. So it will be in this place. It's minus and minus. If it's 2, it's minus 2 plus 3i, it will be here. Minus 2 real plus I2, it will be here. Okay, a number here will be 4 minus 3i. So the real part is 4 plus, and the imaginary part is negative. Okay, this is important too, that you can find out where this number is. It's important when you turn from that form, the Cartesian form, into the polar form. The calculator doesn't help. Okay, so if the solution is, say, z end up being, you know, minus 3 plus I5, where is that number? So you need to know, because you need to generate the theta. And in energy conversion course, this is course they do a lot talk about solar energy and the design of solar panel on the roof, and what's the optimum angle, and where is the sun. And so in one of the design project, a lot of students lost their final answer and dropped from A to a B, because of this, the equation basically gives them the numbers, and when they try to turn it into real and magnitude and an angle, so that they can find out where is the sun, they didn't really realize where is the correct angle. We'll talk about in detail, because the calculator will not help. When you think about it, when you give the calculator those numbers, real, imaginary, and ask for theta, the calculator, the way that you will do it, will not really tell you. You have to basically override the calculator and say, no, I know this guy need to be
Third quadrant. Second.
exactly. So anyway, they end up basically was not half the day, but part of the day there is no sun, but the sun is there, but the calculator showed that no, the sun is below the horizon, and basically the numbers were wrong. Okay, so now how multiplying and adding those complex number. So of course adding is piece of cake. When you add two numbers, you add basically the real parts together and the imaginary part together. For example, 5 plus I3 and 7 plus I2. So it become 12, and you add the imaginary by themselves, 3 and 2, and become 55. Right? Multiplying the two complex number. I'm trying to remind you, when you multiply basically in just two brackets, how do you do that? It's AC plus BD plus BC plus AD. Right? Like this, x squared and minus 3 and 5 and minus 3x and plus 5x. You all know that. So now the trick is that when we multiply two complex numbers, we'll just treat them like this, right? So 5 and 7, 35. But when you multiply this and this, I3 times I2, you get 6 I squared. And I squared is negative 1. I squared is negative 1. So basically, this and this, those become real number. 35 minus 6. 35 minus 6. And when you multiply this and this, the I stay, and this would be the imaginary part. Right? So it becomes 21I plus 10I. And that would be the imaginary. So multiplying those two guys together become 29 plus I31. Question about this? So this is, I basically, anytime I want to multiply two numbers, I just basically use this, it's a piece of cake. But there is this formula that if you want to use, I think it's actually more confusing than helping. It's basically saying that the real part of the multiplication is due to the x1, x2 minus y1 minus y1, y2. And the imaginary part is coming from y1, x2 and x1, y2. I rather just get the four term like this and have I square and turn the I square into minus 1 and build the real together and imaginary together. But it's totally up to you. What we need from you is basically at the end you give us the multiplication results. Right? So now if you do this in MATLAB, you have to remember that actually, or you need to know that MATLAB wouldn't accept x plus I y like our textbook. You cannot tell him 5 plus I7. You have to tell him it's 7 plus 3I. So you have to put the 3 before the I. If you give him I3, he will not understand it. Alright?
Makes sense, because I've never seen the I written first. This is the first time.
Right.
Well, it's in our textbook. This is the way he writes it. So anyway. Okay?
So contrarian.
Yep. So again, this is the real part and this is the imaginary, and you can get this from MATLAB too. You basically, if you give him a complex number, you tell him what's the real of the complex number, what's the imaginary, he will give you the two components of the real number. Subtraction is the same like addition. Again, go with the real part together and the imaginary together. So this guy minus this guy, of 7 minus 5 by itself, and the 2 minus 3 by itself. Okay? And by the way, the addition, when we add all the real part and all the imaginary part together, it's really graphically as if you're adding two vectors. It's like two vectors. And so how you can add vector z1 and vector z2? You know, you basically move this guy over here, and if this is Z1 plus Z2, this would be the addition. Right? So tail to head, and basically that's the. And the subtraction, when you say Z1 minus Z2, it would be as if you are saying Z1 plus minus Z2. So if this is Z2, then this is minus Z2. And so if I'm saying Z1 plus this guy, Z1 plus this guy, that would be the Z1 minus Z2, or Z1 plus minus Z2. Questions? Very good. Now the division is a little bit complicated, right? So how are you going to divide the two complex numbers? Like this, for example, 8 plus 3i divided by 9 minus 2i. How are you going to divide those two guys together? So you multiply by something called first the conjugate number. What's the conjugate number? X plus iy, its conjugate is x minus iy. It's basically the mirror image across the x-axis, right? It's the guy down there from it. So 5 plus 2i has a complex conjugate of 5 minus 2i. What's the big deal about those two numbers? Why do we care about the complex conjugate? Right. If you multiply them, so by in this book they give the complex conjugate the par. Others give them the star. They put a star on top, then that means that this is the complex conjugate. But anyway, if you multiply the number by its complex conjugate, you can see that you will end up with x squared plus y squared, because again I times I is minus 1 and there's another minus. So it becomes x squared plus y squared. That's the real part. Now let's go for the complex part. The complex part will come from x times minus yi and iy times x. So obviously it will cancel. So when you multiply the two complex conjugate, or the number and its complex conjugate, you will end up with only a real number. And that explains to you why when you are trying to divide two numbers like this, 8 plus 3y divided by 9 minus 2i, why you will multiply the whole thing, top and bottom, numerator and denominator, by the complex conjugate of this. Why you are doing it? What's the whole idea?
Get a real number on the
To get a real number at the bottom, to get 7 there. And if you get 7 there, let's just divide everything on top by 7. We are done. We have our complex number on the top. Okay? So, see, when he is trying to divide 8 plus 3i over 9 minus 2i. So you multiply by 9 plus 2i and 9 plus 2i. If you multiply the numerator and denominator by the same number, you didn't change anything. Correct? It's as if you're multiplying by 7 and divide by 7. So, same thing. But with this trick, this guy, 9 times 9, 81, and 2 times 2 is 4. There's I squared, which is minus 1, and there's another minus that make it plus, and the complex number will disappear, and you'll end up with 85 at the bottom. On the top, we know how to do the top, right? Real was real, and imaginary was imaginary, and real plus time imaginary plus imaginary time real. You get this, divide over 85, everything by 85, and use your new complex number. That's the result of this division. Questions? Make sense? Very good. So now the real problem, you know, when he will ask you to basically calculate the complex number. So it has to do with a lot of the problem. Basically, the solution will remain, or the solution will depend on turning things from Cartesian to polar coordinates. That will help a lot in things like this. Right? So any complex number that's basically have imaginary and real and imaginary number, x plus iy, can also be written with the angle and the magnitude, where the magnitude here is obviously x squared plus y squared under square root, right? And this angle is the tan, this theta is basically this guy over this guy. So tan theta is y over x. Okay, and so this is where the problem is, tan theta. That's what I was telling you about the people in energy conversion, that they had problem with their solar panel calculation. So imagine if you have basically -3 plus -3i, and we are trying to find the theta, you will say, well, theta is tan minus 1 minus 3 over minus 3,
Yeah.
right? So you will give your calculator basically tan minus 1, 1. And the calculator would say theta is 45 degree, right? But you know it's not 45 degree. You actually know that complex number. -3 and -3, that's basically this guy. Alright? So you actually have the same tan as this guy. So this is theta and this is theta plus pi. And so actually it's up to you to figure out that no, theta is not 45 degrees. Theta is actually 45 degree plus 180. Okay? And by the way, I'm saying 45 degree, but actually that theta need to be a number, not a degree. Meaning that we shouldn't write 45 degree. We should write
Right over 2
I over 4.
pi over 4. Okay, so that theta is a number, not an angle. So it's pi over 4. If it's not this guy, of course ours is going to be pi over 4 plus pi. Because of the minus and the minus. We'll talk more about it. But basically this is the magnitude and this is the angle of that complex number, right? And so that the number z can be written as x plus iy or r e to power I theta. Alright? And so it follows immediately that x is actually r cosine theta and y r sine theta. So therefore z actually is also r cosine theta plus I r sine theta. This actually formula is called the Euler formula. It's very famous. But you already have proved it right now. You don't have to memorize it. I mean, just from this drawing, you know that r e to power I theta is also r cosine theta plus I sine theta. Okay, and when you think about it, so that's why then, if you do this guy square plus this guy square under square root, you will end up with r. Right? Because again, cosine square theta plus sine square theta is 1. So all the way lead to Rome, basically. I mean, all those formulas, when you start with one of them, you end up with the other two. What are the three formulas we're talking about? That x, z can be x plus iy, z can also be r to power multiplied by e to power I theta, and the relation between r and theta and x and y is this. Those are the three things that I'm talking about. Okay? This is important because this is how you will be able to solve the problem that you'll get in the final. That how you will get the z out of the equation. It's by converting from Cartesian to polar or from polar to Cartesian. Question about this? This tan theta, we'll talk about it in the next in coming slides. How you get the right theta. Right? So basically, I'm trying to say that when you actually come up with the z in polar coordinates, and you would say it's 4 to power e to power I by 4. If that's the solution, that's not the only solution. Z can also, for the same x and y, for the same x and y,
Be the minus.
can also be pi over 4 plus 2 pi. What does this mean? For any complex number, if I told you find the solution for me in the form, if I ask you for the form basically x plus iy, and you said, well, z is 1 plus I, you are done. But if I said find the solution in the form r plus I theta, and you did your calculation and end up being basically that z is 3I pi over 2. That was the solution. That's not good enough. You actually have to say pi over 2 plus 2 pi. Actually plus 2 pi n. Meaning that anything like this can actually work. Why? Because sometimes there is not one unique solution for the problem. And you have to give them all the solutions. Right? So all those guys will if the first one did it, adding 2 pi will also do it. Adding 4 pi will do it. Adding 6 pi, any combination of over here, is that what I'm saying? Any combination of n 2 pi will also do it. And then you would say n where n is 0 plus or minus 1 plus or minus 2. So that's the whole basically spectrum of solution that solves the problem. Right? So if I say find a solution, you give me 1, but if I find the solutions, or find the solution is all those guys. Alright? Because again they repeat themselves on the polar coordinates. It's the same number again and again and again and again. Alright? So you're saying the argument of z is basically whatever you got, whatever the theta that you got, plus or minus 2n pi. Alright? And this is what I wanted to talk about when I said that the calculator is not good enough. 10 minus 1, you see this number, minus 1 minus I, and you are saying, well, let's get theta from the calculator. 10 minus 1 over minus 1. Again, it's 1, and the calculator will be tempted to give you 45, but you should know better, and basically you should add the theta to it.
Knowing what coordinates.
Right, from the sign. Right, so that you know that it's minus and minus, it should be here. Right? And actually, let's also talk about the second and the fourth coordinate. Also, there is a problem there too. So if say z is 3 minus 3 plus I5, the calculator will basically go for 10 minus 1 and it's y over x, 5 over minus 3, and this is exactly the same angle that you will get for also z equal 3 minus 5I. In both cases, if you try to come up with the theta, you will end up giving the calculator 10 minus 1 minus 5 over 3, which is minus what? What's 5 over 3? That's 1, 20 over 3, that's 7, 1.76666.
Yeah.
So if you give the calculator this number, the calculator will probably tell you,
Let's see. Negative 59.03.
minus 59. And in radian, so before the exam, better put your calculator in radian, don't leave it on degree. Right? So what is the number in radian?
Yeah, last time I changed my calculator to radian in here.
It was a disaster.
I went back to compressible and I took the second test and with it in radian mode and got it.
So switch it after you take compressor. Right. Okay.
Negative 1.03.
1.03. All right. So now, depending on whether we have this guy or this guy, okay, we will either end up with this minus theta, or we actually should have this. But actually, the angle here would be 180 minus theta, or pi
You can't
minus
say
theta.
180 if we put it in radian mode.
Pi minus, correct. I should make it. So this 3 minus 5I, we should basically report theta as minus 1.03. That's fine. Okay. So here theta would end up being minus 1.03. But if we are minus 3 plus 5I and we are here,
So
this angle is not our theta. The angle that the calculator gave us, we need to say pi minus theta to get it. The calculator just gave us this.
we don't have to use the reference as like the right x-axis. We don't have to reference that, so we don't have to say like.
If you-
3, we don't have to say.
If you are saying, do you only have to work between 0 and 360 or 0 to 2 pi? No, you can go from 0 to pi and 0 to minus pi. That's fine too.
Okay.
0 to minus pi, that's fine. Right? And so that's why this is okay to say minus theta rather than say, or minus 1.03 rather than saying, no, let me add 2 pi to this. Okay? Does this make sense? So what I'm trying to say is that the calculator will always give you this guy or this guy, and it's up to you to basically either say 180 minus the angle or 180 plus the angle or just the angle here and here. Okay, so there is 180 that you have to play with, or pi that you have to play with. Okay, so theta plus pi in this place. Right, and that was from 4263 when they basically didn't calculate the angle right. Right, so you can find out where is the sun basically based on two angles. When you think about it, the sun position in the sky can be determined by two angles, only two angles. How far it is from the south and how high it is from the horizontal. And that will tell you where is the sun at any point. Right. Different books give them different names. Very good. So, of course, adding will generate a number that's basically less than the magnitude of each one of them based on this triangle. Right? Less or equal. In case you are adding the same number twice, then it will be exactly the same. Right? Very good. So, I don't think it's a really great idea to multiply in the polar coordinates. I will turn it into Cartesian, but anyway. So the way to do it actually is you can actually multiply the magnitude together and you add the angles together. So if you get confused, just turn it into Cartesian, do multiplication easier there and come. But already you just add the two angles together. So the multiplication will end up basically be this plus this, and those numbers basically get multiplied. Right? So the magnitude is R1 times R2, and the angle sitting there would be e to power I theta 1 plus theta 2. If it's easier for you to remember this, do it. If not, just do the multiplication in the Cartesian coordinates. Okay? Somewhere in chapter 13.
Your help.
Yeah.
6:15.
6:15. Right, now let's go to section 13.5. That's where the fun starts. Alright. So the exponential function is not this. This is how the complex number can be written. That z is r to power multiplied by e to power I theta. The complex function is this. When you have e to power z, what is this number? Okay. So it's basically when e is to power 3 plus I 5, for example. I would like this number in the form x plus iy. Because this is a complex number. E to power I plus whatever, 3x, that's a complex number. So what is real component and what is imaginary component? It's not the 3 and the 5, right? It's not. So how we can find those guys? So first, we'll do this in the next page. But in this page, he's just trying to remind us that any complex number can be written as magnitude plus or magnitude times e to power I theta, where theta is the angle. Can also be written as r cosine theta plus I sine theta. Alright? So obviously when you think about it, then that e to power I theta is cosine theta plus I sine theta. That's the Euler formula. E to power I theta is always cosine theta plus I sine theta. E to power I 7 is cosine 7 plus I sine 7. E to power iy is cosine y plus I sine y. Yes.
So is the r e cubed and the theta is 5 radians?
Say that again.
The r is e to the third and the radius, then the theta is 5 radians.
I didn't get it. Say that
So
again.
is the r e to the third and theta is 5 on your example on the board?
Over here?
Yeah.
No, we didn't say what. This is just a complex number, right? So if you want to say this is e to power what exactly? This will be 3 plus 5 square under square root, right? E to power I.
Could you write that as e cubed times e to the I 5?
Yes, I can. That's what we'll do next page, right? That's the solution. That's the solution. Following from this fact that e to power iy, then is a complex number with this real and this imaginary. Okay? Right? So e to power iy is cosine y plus I sine y. So that's why Jason is saying then, so if this guy then is e to power 3 multiplied by e to power 5, we know this, right? Because we said, you should know that it's simply e to power theta 1 multiplied by e to power theta 2. That's why when you multiply them, you add the angles. You add the coefficient. Right? So he's saying that this is basically those two numbers. And I just said right now that this is a complex number with a real and imaginary part, right? What's the real part? No.
It's cosine 5.
Cosine, right? Cosine 5
minus I sine 5
plus I sine 5. So that's just this part. And this, what is that? Is that a complex number or a real number? Just a real number, right? Which is e to power 3. It's like 7, I don't know. Let's do it in the calculator. E to power 3. What's e to power 3? 2.7, multiplied by 2.7, multiplied by 2.7. How much?
20.08.
20 point something?
20.08.
20.8. Right? So then this guy must get multiplied by this. Real time rate, that's another real. And real time, this number. It's like you are multiplying the whole thing by 7 or something. And you got your real plus I imaginary. We'll see it in detail next, but just make sure that you are really comfortable with this equation or this relation. So e to power I something is cosine this something plus I sine this something. Right? Good. So again, e to power I an angle, that's a complex number with imaginary or real. Actually, based on the angle, sometimes you can tell that this number is just imaginary or just real. For example, e to power 2 by I. You will do cosine plus I sine, right? So cosine 2 pi plus I sine 2 pi. What's cosine 2 pi? 1. Because 2 pi is like 0, right? It's like as if I'm telling you cosine 0. So e to power 2 by I, whatever this thing is, we said this number can be written as cosine this number plus I sine this number. Sine 2 pi, that's 0. Cosine 2 pi, that's 1. So basically this guy is 1. Alright? So that's real component 1 and imaginary component 0. How? Just the rule, just apply the rule. Whatever this number, it's cosine plus I sine. Right? But your eye will slowly start to catch up, and basically you can tell yourself, for example, e to pi I. The other way that you don't have to apply this formula, but your eye can tell you immediately, is that when he basically say e to power pi I, you should imagine as if you are looking at looking at 1 times e to the power by I. And now this number is in the form of r e to the power
I theta.
I theta. And so obviously the r is 1 and the theta is pi, right? And that number is, right, minus 1, right? Just by saying, well, here this is a magnitude, but I don't see it, and here is the angle. If you don't buy it, just cosine plus I sine, and you get the real and imaginary. Either way, you will get your number. And for the same reason, you can see why e to minus pi over 2i is minus I. Because again, the magnitude is 1, and the angle is minus pi over 2, or basically this way. So it's like this guy here. That's minus I. Plus I minus I. Okay, questions? E to minus pi I, that's basically this guy, actually over here. E to minus pi I, it's like this. Again, it's minus 1. So e to pi I and e to minus pi I, both of them are minus 1? Yes, because this number is also by I plus 2 by r or minus 2 by I. It's the same thing. Right? It's the same number. E to power pi I is the same as e to power pi plus or minus 2 by n. You can add any number of n you want. Right? And from the point of view of that, you know, going to this place, you can go, this place is basically this number here. You can go this way or go that way. If you go this way, you would think this is e to power pi. Huh? And if you go that place, it will be e to power minus pi I. So either way, this number is minus 1, minus 1. Any way you want it. You want to use the formula cosine pi and sine pi, go for it. You want to just imagine this is the magnitude 1 and here is the angle I'm looking at. You will see it also. Good. Complex number is the reason why I almost hated fluid mechanics, but I didn't, fortunately. So I kept going. Alright. Now here is the e to power z. Okay? And so he's basically saying can also be written as exponent z, and this can actually be written like what Jason did for us earlier today. You can look at the z and basically saying it's x to power e to power I, so that z is x to power iy, and therefore you can split it into e to power x times e to power iy. Because again, when you have e to power something multiplied by e to power something, all you have to do is just add. So it becomes x plus iy. But now when it's like this, e to power iy, that's the formula for e to power y, and e to power x is this guy. So that's the first problem you should expect, or kind of problem that you expect. If I tell you e to power z is 7 or something, you will break it into this, you will equate it to whatever I'm giving you, and you will figure out what's the x and what's the y. Okay? Very good. So let's actually take a 15 minutes break, and we'll continue after the break.